If you ask a person to give you a number at random, odds are they are going to say 7. This is especially true if you ask them to choose a number between 1 and 10. 1 is too much of an outlier, and so is 10. All of the even numbers are just too ordinary. We're just too used to 3 and 5, and 9 isn't even prime. And so we're left with 7. This has nothing to do with mathematics, but it is handy when discussing today's topic. The Collatz conjecture. Why is 7 so handy for discussing this theory? Well, first, what is it? The Collatz conjecture is an unsolved mathematical conjecture concerning a function that consists of two rules, one for even numbers and one for odd ones. Any number that comes out of the function is then put back into the function, and the correct rule is once again applied to it. If the number is odd, multiply it by 3 and then add 1. If you do this with 7, you'll end up with 22. It's worth noting that this process will always give you an even number. If the number is even, however, you divide it by 2. Doing that to 22 gives you 11. If you do this over and over again, applying the appropriate rule to each successive number, you end up, in this case, with 1. The conjecture is as such. Any number that is whole and is greater than 1, plugged into this function, will end up reaching 1. On the surface, this might seem fairly simple, but as you dig deeper, you will find that proving or disproving this theory is nearly impossible. The Collatz conjecture gets its name from German mathematician Lothar Collatz, who originally discussed the problem. The series of numbers produced by the function is also known as the hailstone sequence, due to the fact that the numbers rise and fall dramatically before falling to 1, like hailstones in a cloud. If you look at the graph of the values you get when you plug 7 into the function, you will find that it is quite different from its neighbors on the number line. This lack of a pattern is what makes the problem so hard to solve. The Collatz orbit of 7 is the sequence of numbers that you just saw graphed moments ago. It is the sequence of numbers produced when you plug 7 into the function. The total number of steps it takes for a number to reach 1 is known as its stopping time. 7 has a stopping time of 16, but this graph once again shows that while there are some patterns in the stopping times of numbers, there is no evidence towards a pattern that is consistent enough to allow us to predict what numbers will reach 1, and if there are any that won't. The most commonly sought after result in the researching of this problem is a counterexample. This begs a pretty simple question. What would a counterexample look like? Well, there are two options. The first is what is known as a divergent series. This is an endless string of numbers that never repeats and never reaches 1. The other option is a loop. There is already one loop consisting of 1, 4, and 2, but a loop that is a counterexample would repeat forever while still never reaching 1. While neither of these look particularly appetizing and neither of them have been proven to exist, there is still a good amount of proof towards the unlikelihood of an endless series. Let's take a look at what that is. Chinese mathematician Wei Ren has proposed a new approach called the reduced Collatz conjecture. While the original problem asks if all numbers reach 1, the reduced version simply looks at whether or not the number results in a smaller number. This might seem trivial, but Ren then proves that the reduced Collatz conjecture is actually the same thing as the original. Look at it this way. If all numbers result in a value less than the original number, then you could substitute the new lower value for the first one, giving you a new even lower result. If you do this forever, the values will eventually decrease to 1. But how do we know if each number does actually lead to a lower number? In fact, such a thing has been proven. Sort of. Take any odd number. We'll call this first number n0. After plugging it into the Collatz function, it will become an even number, and then at some point output a second odd number, n1. It is provable that, in fact, this number will on average be around 3/4 of the original n0. How does this work? Well, it is provable that n1 will be equal to 3 times n0 plus 1 divided by 2 1/2 of the time. Likewise, n1 will be equal to 3 times n0 plus 1 divided by 4 or divided by 2 twice, a quarter of the time. You'll be able to divide by 8 1/8 of the time, divide by 16 1/16 of the time, and so on, as long as you continue working with powers of 2. But why is that? Well, let's look at some numbers you're familiar with. If you look at every even number between 1 and 48, you will notice that half of them are evenly divisible only by 2, not by any larger power of 2. If they were divided by a larger power of 2, the result would not be a whole number. If you look at the remaining numbers, you will find that half of them, or a quarter of the original set, are evenly divisible by only 2 or 4. Another half of the remainder of those are evenly divisible by 8 as well. Then half of the remainder of those are evenly divisible by 16 as well, and so on. The number of even numbers divisible by a power of 2 is going to be half the number of even numbers that are divisible by the power of 2 one less than that one. If you discount the adding of 1, which you can do with very large numbers, you will find that the ratio between n1 and n0 is 3 over 2 half the time, which can be represented by 3 halves to the power of 1 half. That ratio will be 3 over 4 1/4 of the time, 3 over 8 1/8 of the time, and so on. If you multiply all these probabilities together, for every possible power of 2, you will approach a limit that is equal to 3 over 4. That is what the ratio between n1 and n0 will be. And because we know that 3/4 is smaller than 1, we can hypothesize that plugging any number into the Collatz function will lead to a decrease over time, proving the reduced Collatz function and therefore the Collatz function as a whole. Did we just do it? Does this mean there's hope? Sadly, no. I'm sorry. You may have noticed that I used the word almost in there a couple of times. Due to the fact that 3/4 is just an average, this is only a slight bit of evidence against an infinite series. These sorts of almosts are all over the place when it comes to Collatz. Math prodigy Terence Tao published possibly the most important work in all of the history of the conjecture in the form of a paper titled, somewhat comically, "Almost all orbits of the Collatz map attain almost bounded values." Ilya Krasikov and Geoffrey Legrarius were able to prove that the number of numbers that will reach 1 between 1 and x for any sufficiently large x will be equal to roughly x to the power of 0.84. While this does tell us that there is a limit as to how many counterexamples there could be, like so much other evidence, it is simply not enough to tell us whether or not we are there. So why bother studying the Collatz conjecture? Why should anyone care? Well, first of all, it's understandable. While much of the research is insanely complex, and the results even more so, the actual problem itself is fairly simple. When starting off by simply looking at the rules at hand, even I, a lowly high schooler, can look at it and give my opinion, even if I am never going to be the one to solve it. The second reason is that it's important. Famous mathematician Paul Erdos once said of the conjecture, quote, "Mathematics may not be ready for such problems." And while many others have said similar things, we must remember that we are living in a time where increased computing power is allowing us to push the limits of what we can calculate. And some of the greatest math geniuses of all time are still alive and putting out work. Again, I am not going to solve the conjecture, but nobody else has, so if I can at least look at it, why not? These reasons may not be much, but I believe that they make this problem worth looking into, not just for the legendary problem solvers of our time, but for everyone.